This video is the capsule 2, so unit 2 for mechanics at John Abbott College. So I'm explaining everything that we learned concept-wise and sometimes showing some examples for mechanics. And this is a unit 2, so the unit 1 is another video. Unit 2 is all about forces and torque. Well, torque is like force but in rotational. So there's a lot of linear and also rotational situations where there are forces applied in different standards of different directions, gravitational forces and acceleration. And I'd say it's probably the biggest unit in mechanics. The first one being kinematics, so like movement. So the second one's dynamics, all the forces that create these movement. And the last one is work and momentum. So there are conservative stuff, conservative energies, and conservative momentums. So everything started off with Newton's law for the unit 2. And the Newton's law is, there are 3 Newton's laws, and you basically need everything. So first one being anything that is moving will stay moving. There's a whole definition and like a better way of saying it, but the whole point is that moving object stays in motion unless acted upon by a net external force. And a net external force basically means forces added up together that don't cancel out. So a force that's going that way and a force that's going that way, well, this does not cancel out because there's a net force slightly going that way. If there was a force going that way, and another going that way, well, these two, let's say, cancel out because they're equal in magnitude, but this one don't. So this is net external force. That's what net external force means. And it's really important because we also use that in the second Newton's law. So this is Newton's law number 1. Because number 2, the second law is F net equals to ma. M is the mass and a is the acceleration of a object. And F net again is the key word here because it's not any force or the sum of all the forces. It's the sum of forces after basically canceling out what is originally there. So this one would likely become, well, this one canceled out slightly for this one, but some remain. This one totally canceled out, but some of that remains. So it will end up looking like that, and the sum of this force will end up looking like this because of vectors of sums of vectors. So that's the F net in this case. Either way, you will be learning a lot about free body diagrams and force diagrams. So right now you just need to understand that force net equals to ma, and that's your go-to formula. And that's like basically the most important formula and the most dependent formula you'll be using. The third Newton's law is action-reaction forces. They are equal and opposite. And this is vector-wise. Forces are vectors. Vectors meaning they have direction. They have a magnitude and a direction. Magnitude is like how strong that force is. It could be like 5 Newton, it could be 200 Newton, and direction is, let's say, 260 degree. Oh no, that makes no sense. It could be like 331 degree. It could be a 25 degree. So it's like a vector that has like a length. Usually the length when you draw it should be proportional to the force. So let's say this is a 50 Newton, and that's at a 25 degrees. So vectors are always coming with magnitude and direction. It is really, really important that you understand vectors in the entire mechanics course, because you really have to be super good at vectors, component wise and polar form wise. So vectors have component form, and polar form. So the component form is basically the x and the y's coordinates, and you do not need, no need for an angle, no need for a theta. But this one, the polar form, you need the magnitude. You'll give the magnitude and at a third in degree. So you're gonna have to give 2 answers, and depending on the question, you have to give either one. It's not always you choose whatever. It's asked in the question. Otherwise, you can choose. But if you are choosing, you cannot forget to add your angle if you're only saying the magnitude. And I'd say most cases the answers should be in polar form, just because that's simpler and that's more clear, and it shows really that you know that you have to add a direction. So adding direction, you should never forget it. And there are many types of directions, not only degrees. Sometimes it's in K form, J form, and I form. That just means X. In X, this just means in Y, this just means in Z. Should have wrote it in X, Y, Z. But basically, sometimes you just need the negative signs, meaning that it's a vector going that way for negative I, vector going that way for negative J, and could be looking like this for negative K, because K is like a Z. It's like a 3D, third dimensional, and there is a few third dimensional questions in, especially in torque in mechanics. So those are a few ways to write your some vector answers. And action reaction forces, coming back, is all about whatever that's been pushed. Usually a pushing force, let's say a man is pushing on a box, the force that's been pushed, it's equal and opposite as the force that the box will push on a human. That's basically what it means. Anything that's exerting a force on an object, so let's say a ball, and this is the earth. A ball has a gravitational force towards the earth, that's why it falls. At the same time, there is the opposite action-reaction force from the earth towards the ball, and those are equal in magnitude and opposite direction. And opposite just means if this is 270 degree, then that is 90 degree, because they are opposite angles. So if there's something that is at, let's say, 20 degree here, well, the opposite action-reaction pair should also be a 20 degree from the 180. So 180 plus 20, so that'll be a 200 degree. And that's the whole concept. And this one is really useful because there could be situations that they don't give you as much information. However, as long as you know the third Newton's law, stuff like two objects being exerted a force F, and you want to find out the internal force, let's say that this box feels, then, well, you know that if you're given other details, because this is just an example for proving the Newton's law, if you have the force that is given to you and you know what force the B is exerting on A, well, you know that the A is exerting the same force towards B, but it's just in different, well, the opposite direction. And you know that this one's equal to this one in magnitude, so there are other calculations that you can do afterwards. That's just an example for explaining the Newton's law. After Newton's law, there's the inertial frames. This one, it could be deeply looked at into in the momentum chapter rather than the F equals to ma, but it is a bit relevant. Let's say there is a plane or train. Let's say this is a plane, and you're standing in the plane. There's a ball, and the whole concept of inertia or inertial or non-inertial frame is about when something starts accelerating without any force acted on. So if this ball starts moving when the airplane starts going forward, well, you know that this is a non-inertial frame. And that just means that the objects that are on the plane, in this case, that's the frame, is not synchronized. I'd say that it's not in the same inertial frame as the plane. So that sounds a bit confusing, but basically it means that the ball is more synchronized with the earth. So the earth and the ball are in the inertial frame because the earth is moving, but then the ball on the earth will it's all about reference point. The ball has a reference frame to the earth, so it will look like the ball on the earth, like on the ground, will not be moving. Like the earth is rotating, but the ball on top of earth looks like it's not moving. It's kind of same thing as a human standing. Let's say you're standing on the ground. It doesn't look like you're moving because it is in reference to the earth, and the earth is just so big that when you're on earth, it doesn't look like you are moving. It is a bit different. Well, it's the same concept, but it looks different on the airplane. Let's say if you're standing on the airplane and you're not moving when the airplane is moving, well, it looks like you're not moving as long as you're on the airplane. But if you're outside of the airplane, let's say a human that's standing on the ground and looking at you from the bottom and looking at you up the sky, well, it looks like you are moving totally because you're in the plane and the plane is moving and you're moving with the plane. However, when we talk about inertial or non-inertial, we're only looking at the frame in context. So if a human is standing on an airplane is not moving, well, then the human is in an inertial frame with the airplane. So in this case, let's say the ball is not moving, and the human is also not moving. Well, then they're both in an inertial frame. The airplane is an inertial frame for both of these objects. Well, human and the object. In this case, if the human is not moving, but the ball is, well, the ball is not in an inertial frame. So the ball is in a non-inertial frame. So then what causes the ball to move? It's the acceleration. The acceleration will cause the ball to move due to change in motion. Well, it's acceleration of the airplane. If the airplane accelerates, well, the ball has a reference inertial frame to the earth, then obviously it does not stay immobile on the earth, on the plane. It's kind of a logic. If you see a ball that starts rolling on the train without anything moving because the train starts moving forward, well, it's because the ball itself wants to remain in place, was referred to the earth. It wants to stay in place. But the acceleration of the object that it is on, so it's like a plane or a train, is not in accordance with the ball. So when it is and it is not moving, then it's a reference inertial frame. And when it starts moving, it just means that it is in a non-inertial frame. The inertial and non-inertial is just for you to understand that F equals to ma has to do with the a. So anything that moves, so moving basically has to happen from the force. Anything that moves has to go through an acceleration and not a constant speed. The key here is that if the airplane was going forward at a constant speed, the ball will not be moving. If the ball was on a train that moves at a constant speed, the ball will not move, will not roll. And when it is in a non-inertial frame and it does roll, that is because the airplane is accelerating rather than just going at a constant speed. And when there is a constant speed, we call that zero net force. So F net is 0. doesn't mean that there is no force applied onto the ball. There is forces, actually. There's always the gravitational force and the normal force if the ball is at rest and if the ball is not flying or sinking into the earth. So when the ball is not moving, it just means that F net is 0. Let's say there's some sort of force, let's say a wind force going that way and a friction force that way. Well, the total force is balanced out, and the net, or the total force summed up together, is 0. Then it is in an inertial frame because there is no force that is trying to move the ball. So we can go into the free body diagram. Free body diagram is basically the diagram of all forces that are acting on an object, and a very simple one could be a box. There is the gravitational force, which we write Fg, the normal force, which is N, which is an action reaction. So these two are action reaction, Newton's third law. And well, let's say that's it for this one, to be a very simple case. There are many cases where you're gonna have an inclined plane, and there's gonna be an object where you'll have, as per usual, the gravitational force and the normal force. And what's different here is that the normal force is a bit tilted, and that is because of the angle right here. The normal forces always have to be perpendicular to the surface. And what causes a difference in here is the angle. So if there is an angle, other forces that are acting on it will have to match the angle accordingly. So let's say there is a theta here. If you know your triangle properties, we'd want to draw your x and y components of the gravity. So this one's going to be Fg and y, and this one will be your Fg and x. What this means is that if your plane is xy like that, there is a gravitational force in the x-axis over here and in y-axis over here. And the theta here is the same angle right over here. Because if you look carefully, this is theta and this is 90 degrees. So this is phi, let's say. And then if that is the opposite, well, 90 minus theta, okay, sorry. This one is going to have to be 90, and I forgot how to explain this. Oh yeah, sorry. This, you just need to prolong it. And if you prolong that, you will see that this angle will have to equal this angle, because I should have wrote it in a different color. The orange angle here has to equal to this orange angle here, because they are it's a property of angle, same angle and same same two angles will result in the third angle, since everything has to equal to 180. There's a theta here and there's a 90 degrees, so this one has to equal to this one here, because they also have a 90 here and the same angle over here. Either way, this one will end up the pink angle, and you can just draw it with triangles. And if you remember your triangle properties, figuring out which angle is what is quite simple. But I'd say definitely prove yourself before moving on, because if you have the wrong angle, it just result in all your calculations being wrong. So if I would add other components to this drawing, there is in most cases friction. So let's say this movement is going that way, like it's falling. If it is falling, there has to be a force going that way, which is the friction force. And if it is in motion, it's a Fk. So friction is a whole new concept that we don't learn in high school normally. There is the F static and F kinetic. So that's static friction and that's kinetic friction. F means friction. And they also have their individual formulas. F static is mu s times the normal. Normal is the magnitude of the normal. And this one is always equal to mu k times n. These mu s and mu k, they are a constant. So they are constants that come from how much does it rub on the surface. Let's say there's a surface right here and you're trying to move this block, and how much it rubs on the surface depending on the quality of the surface, depending on the material of the surface and of the object, and how fluid it moves, how smooth it moves. The bigger the mu's, the rougher the surface, so it's harder to move the object. And we're saying that a static friction is less than or equal to, because static friction basically means a friction that is keeping the object in static state, meaning that it does not move. Let's say on an inclined plane there is a ball, there's a box that does not fall. It does not fall. That means there's a friction force going that way, because if you think carefully, if it's trying to go that way, this is logic-wise, not really physics-wise. If it's trying to go that way, there has to be a force that's opposing it going forward. That's why it does not fall. And the force that's trying to go that way is actually the gravitational force, but in the x plane. There's an x gravitational force in x and a gravitational force in y. This is the FG. And this friction will have to oppose the friction in x, the gravity in x. But it's not only the gravity. There are other forces that will come in, especially if there are other components in your situation. But you should always remember that friction force is parallel to the surface, no matter what kind of surface. So the friction force in this case is right here. It's again parallel to the surface, and it kind of makes sense. Actually, totally makes sense, because friction always happen on a block or any object along the surface. That's why there is friction. So remember that normal forces are always perpendicular, and friction forces are always parallel. And Fs, like I said, is when it's static, so it's not moving. So everything balances out, and F net, once again, is equal to 0, because there's no acceleration, there's no movement going on. Everything will cancel out. All that vectors going up and down, left and right, will just all cancel out, and the net force is equal to 0. When it is not equal to 0 is when the object is moving, and that's when we have the kinetic friction. Kinetic friction means a friction that is acted on an object that is moving. Let's say there's an object, and this time it is falling. It's falling, so it's going that way. It's accelerating that way. And again, we have our FG, and we have our x components. X components of the gravity and the y components of the gravity. And of course, similarly, there is a friction, but this time the friction is a Fk instead, because when it is moving, it has a different magnitude of friction when compared to when it was stable, so when it was static. And that's where we have the logic. You have to know that the static friction is always bigger than the kinetic friction. So the mu s is always bigger than the mu k. Yeah, so the coefficient of the friction of static is always bigger than the kinetic. And that is because the mu k is always equal. It's just equal. No matter how fast it is going, no matter if it's accelerating slowly or quickly, no matter if there is no acceleration, as long as the object is in motion, it is constant mu k. So the coefficient of friction is the same. You have some questions like a box that is moving, that is accelerating, and there's a friction, and there is a ball that is going forward is a constant speed. This one's accelerating, this constant speed, and another one that's like acceleration, but a negative acceleration, so it's slowing down, a speeding up, and a constant speed. And they'll ask you which of these kinetic frictions are, well, order them in the increasing, like put them in increasing order, decreasing order of your Fk, or the force friction K. And the answer is they're all the same. Like I said, because no matter the velocity, no matter the acceleration, no matter if it is a positive or a negative acceleration, if it's slowing down or speeding up, or that it has no acceleration, the kinetic friction is always the same formula. The mu k will always be the same. The normal could be different depending on your case, but as long as you apply the mu k, it is always constant. And what matters here for the static friction is that you don't just always have the same static friction. And this one also comes from a similar logical concept that if you are trying to push a block, and the block is not moving. Let's say you push a block with a 5 Newton. It's not moving, and you also push again with a 50 Newton because it's still not moving. Okay, it still does not move, so you push with a 500 Newton and it still doesn't move. And when you push by a 502 Newton, then it starts moving. What this means that there was friction here. There was a friction here, there was friction here, but there was friction here as well. But every time the friction was getting bigger, because how much you push, this is the certain law for Newton, has to equal to how much the friction is in order to balance out your vector diagrams, because these will have to cancel out. How much you push will change how much friction the box exerts on the surface. And that's also kind of logical. If you're pushing a lot on the object will of course have to oppose your motion a lot. And if you're just pushing a little bit, like a 5 Newton, then the friction is a lot smaller. So diagram wise, there is there's a graph that they will likely show you. It's like this, and then it suddenly drops to some sort of line like that. So this one is the mu s. This one is the mu s with the force friction s, and this one is the force friction k, because at one point there's a maximum static friction times the normal. So the mu s times the normal, there's a maximum static friction, and when you exceed this amount of static friction, so if you exert more force than this maximum over here, then it will start moving. That's why it drops suddenly. It will suddenly drop, and depending on the condition of the surface, the mu k could look linear or wobbly. Most of the time it will look wobbly because experimentally it will never be perfect. But the whole concept is that if you're pushing an object, let's say a pushing object on a gravel street, and the object doesn't fall, and you keep on pushing and at one point it starts moving. So it starts moving. Then from 0 to how much ever the amount of Newton force you had to push, well, that was the static friction. And as soon as it starts moving, it's a kinetic friction. And that, again, is no matter how fast or slow you're pushing it. So this is a great concept to understand, because at the verge of slipping is the keyword that they will always use. The verge of slipping means the Fs is at maximum, so the static friction is at maximum. And if you remember the equation, the static friction is smaller or equal to mu s times the normal. And the normal is what's always changing. Of course, mu(s) could be changing as well, but on the same context. So if you have one context, mu(s) is always constant, mu(k) is always constant. What is not constant is the value of fs that you get from the normal times the mu(s), and that's all about how much force it's applied and how much you're pushing on it. So when it is at maximum, so when the object is on the verge of slipping, the verge of going forward or backward, just the verge of motion, when it's about to start moving from their static state, well, the fs is going to be maximum. We don't need to care about if it's smaller or equal to. It's just straight up mu(s) times the normal. And the normal force is always the magnitude of the normal force. Let's say on the surface like this one, there is a gravitational force going down and there is a normal force this way. You do not take the normal force that looks like is in a vertical or horizontal plane. Those are wrong. Do not use those. You always have to use the magnitude of the normal regardless of the direction. And a good hint for you is that the friction is always perpendicular to the normal. So this normal, since there's going to be a potential x normal or a y normal that you might see and might confuse you, always remember that the friction force, which is this one here, is always perpendicular to your normal, and then you will not mix up with using the wrong normal. Well, the normal is, this is the total normal actually, and it is true that if you have a plane and there is a normal, you could take this as a normal in x and a normal in y. In that case, your gravitational force will just be itself, because that's the plane you're using. In this case, you're trying to use x and y like that, whereas the road has an angle. And this will be really important in the banked curve problems we'll be covering later. But the x and y's in the normal will matter if your axes are in vertical plane, because we only want vertical component, vertical and horizontal vectors on a vertical and horizontal axis. And in this case, you will be using your ny's and your nx's. But when you do want to calculate your friction, always remember that it's neither this or that. It's always the normal that is perpendicular to your friction. So basically the magnitude of the normal that you're supposed to use. Friction is just a part of your free body diagram. So that's like a free body diagram. Free body diagrams should always include all of the forces, and that's usually, and I'm drawing an inclined plane because that's the most common ones. There is the gravitational force, the normal force, the friction, depending on which side it's the friction, what type of friction it could be. And in a free drop or like a falling motion, that's all there is to it, and that's a little bit confusing at the beginning. But let's say that the ball is, well, this box is falling along the street, and there is no force pointing specifically this way, and might seem confusing because F net is supposed to equal to MA, but that's just an illusion, because if you look carefully, there is a component of FG and X, and therefore FG and Y, that after subtraction, if it does move, it means that FG and X is bigger than the FS, and resulting therefore in a net force vector going that way. A Q to your F equals to MA, F net equals to MA, is that the direction of force vector is always equal to the direction of A vector. So if the net force is going that way, the acceleration, regardless of its magnitude, has to go that way as well. So if the ball is falling this way, then there has to be a net force that way as well. And in this case, it's the gravity. Let's do an example of strings hanging a mass. A free body diagram will need your FG, and in this case there are two tensions, T1 and T2. And you also have your X and Y components in these kind of cases as well, where there is a tension 2 in X and tension 2 in Y. This one as well. Tension 1 in X and tension 1 in Y. And it's easier to look at them in component wise, like the T2, Ty, T1X, T1Y, because you can subtract and add with your FG that you have over here. So what this shows, if it is in static state, so if it is not moving, is that things will have to cancel out and will have to be equal to each other depending on the axis. So in axis X, we have a force going that way and a force going this way. And in Y, we have a force going up, going that way up. And we know that T1Y and T2Y will have to add up and equal to FG so that it doesn't go upward or fall downward. And we also know that T2X and T1X will have to equal to each other so that it doesn't go left or right. And this is a misconception if you think that T2Y has to equal to T1Y. That is totally wrong. It's true that T2Y plus T1Y is equal to the FG, but they do not have to be they do not have to be equal in magnitude, and they in fact are not because of the triangles. So there is a triangle that they form and each have a different angle. This is the first triangle, that's the other triangle, and the angles that they form are different. But we also know that T2X and T1X, they are indeed the same. They are equal in magnitude, although opposite in direction. They're the same, they're equal in magnitude because there is no other force in X's. So there's no other force, there's no such gravity that is going in the horizontal direction, there's nothing. The only forces acting on the box in horizontal plane, so the X plane, is the tensions. So tension 1, if it was any bigger than tension 2, then it will be going that way. There will be motion, there will be acceleration. That is not the case. If it is in static, they have to equal to each other, and they're symmetric. Although one looks shorter than the other, it just means that the other components work differently. So in this case, we know that T1 and T2 is different, and that could be found from your triangle identities, such as x and y. So x to the 2 plus y to the 2. You can root that, or just use your angles, and the angles will give you like a tangent of angles equal to x on y on x, or more usually speaking, if that is T2, you would go like T2 cos of theta is equal to x, and T2 sine of theta is equal to y. Where you also have for T1, you can do the same thing for T1, and to isolate one of your t's, you will use this formula, or this equation that you came up with, and this equation that you came up with. You can either substitute or do comparison, or whichever way you can to isolate stuff, and that's just basic algebra. There is something I didn't cover. It's the sum of force notation. So I'm going to come back to this box right here, which is a good example. So like we said, there is T1 and T2, and there is like a X component and a Y component in each of them. There's a notation, well, there is a way to write this properly, and it's this sign over here, this representation right here. It just means sum of all forces. But sum of all forces in Y and sum of forces in X When you write it down like this, it's really useful, and that's like a fundamental way of writing stuff that you need for the whole chapter and the next chapter as well. So what it means is every force in X, we want to write it here. In this case, it will be, if that is the positive Y, and this is a positive X, well, anything that's going this way will be a negative Y. So as a common sense, T2Y plus T1Y minus FG is equal to 0. And that's equal to 0 because nothing's moving. Or it should have been a MA if it was accelerating. The box is the M, or the mass of the box, and A is how much it's accelerating. And I'll show you what that'll end up looking like if there is an acceleration, because the direction of acceleration matters. It matters. In this case, there is no acceleration. Everything is not moving. It's in static state. I don't know how to say it. It's a static situation. So there is no acceleration. In x's, we have a t. 2x minus t1x equals to 0, and it's important that you put t2 in positive and t1 in negative, because you have to follow the axis. So anything that's going that way should be positive, anything going that way should be negative. And it does not matter here because it's 0 anyway, and writing it like this won't harm, because either way you're just saying that t2x is equal to t1x, and regardless of which sign you put, it's just commutative. However, this case, it is fine. It's not always the case, because sometimes you would need the signs to actually work properly so your acceleration matches your equations. But again, this case didn't have any acceleration, so we'll just move on. So this is how you should be writing your equations in the sum of x and sum of y's. Of course, like I said, the t2y could actually be a t2 sine of theta, and that could be plugged into here if that one is a t2 cos of theta. And you can isolate t2. You can look for your unknown depending on the context, but that's just the notation. Let's we have to kind of talk about angular before jumping into the accelerations, since it's kind of relevant in terms of notation. Angular acceleration. So the linear acceleration was what we've been seeing in a motion like this. So this is a linear acceleration. If it is going forward, then there's an acceleration going that way, and that's a linear acceleration because it's just a linear movement. So the movement with the velocity is increasing that way. The acceleration is also linear. But there could be an angular acceleration, which we kind of saw in the first unit. But it is acceleration of a motion that's a rotational or angular motion. Usually coming with the omega. Omega just means velocity in angular form. F equals to ma also applies here, but with specifically a being a centripetal acceleration, which we also saw in the first capsule with angular dynamics, kinematics. There's like the alpha and the AC and the A tangential, and when we're talking about F equals to ma, it is the A centripetal, and that is because the motion, the circular motion, will usually be of constant acceleration, and constant acceleration, or I should say constant velocity, if it is not accelerating at all, so that there's only centripetal acceleration. So yeah, it will be a constant velocity in most cases. What this means is that, let's say this round circle thing was a car. This is a car. And if a car was turning a corner, or like a driving in like a circular path all the time, there is the gravitational force, the normal force, and most importantly, a friction force. and static friction force because the tires are not slipping on the ground. That keeps it rotating. So the velocity in this case is changing only its direction because it's just rotating like that. The velocity is constant and it's just changing direction. So the acceleration will have to point toward the center. And that follows exactly our drawing in the free body diagram because the Fs is the only net force in this case. And if it is a flat ground, so it's a flat road, I'm saying flat because it matters if it's inclined or not later on. If it's a flat road, Fs mu is just equal to mu s times the normal. So normal is equal to the gravity because we know that the normal force take away the gravity force is equal to 0 because it's not moving up and down, and normal therefore is equal to Fg. And if you want the friction force, well then you just need to do mu s times Fg because they're the same. There could be a situation where there's a cone, and in the cone there's a ball that's spinning around, and that's a very similar situation, but in this case the plane will be different. So instead of being a flat surface like on a road, it will have an inclined surface because it's a cone paper that the ball is spinning on. However, the acceleration idea is the same. You have a gravitational force still going down perpendicularly, and a normal force that way, perpendicular to the surface this time, and there is a friction force as well. Yeah, so in this case you should have a plane in the perpendicular and horizontal well, the axis should be in a perpendicular and horizontal axis, in perpendicular and horizontal plane, and that is because the acceleration is in the perpendicular and horizontal, or vertical and horizontal plane. And this matters because you will always want to match your F net to the direction of your acceleration. The net force, whatever that result is, should match the direction of the acceleration because that just makes your math and your calculation a lot simpler. If you were to use the axis this way, which you could say that this is x and that is y, everything's going to be a lot harder and the math is going to be a lot more messier because you will be struggling a lot to find the acceleration this way, which is the same direction as the the vector, the force, some force that is equal to the acceleration. So avoid using axis that is not in the same plane as the acceleration. Acceleration is going that way, then you'd want axis in the same direction or in the same plane. If the acceleration was this way, let's say the ball was falling, not spinning around, then you'd want your axis to look like this, x and y, and you would draw then you will represent your equations accordingly. In this case though, we do have a horizontal acceleration, meaning we want a horizontal vertical plane for our axis. So in x we have nx, and it's not falling, so let's say there is a friction force going that way. Let's say there's a Fs going that way so it doesn't fall, and we have a gravity going down, which is just y. We can actually start off with the y. It's just Fg, and in f of x, sum of x, we have a normal force, which is and in x, like I said, right now we have normal forces with x and y components. It's only the f and the normal in x, and this is a s. The static friction also has components, the x component and the y component, so fsy and the fsx. it will be negative, well, minus FSX, since it's opposing and it's opposite direction of A. So you always want everything positive to be in the same direction as your acceleration. That's what I was talking about when I said that it matters which direction the acceleration is in. If the acceleration is going that way, all your forces that are pointing that way should be in positive, and pointing opposite should be in negative. The friction force right now in X, so FSX, is pointing opposite direction of our acceleration, so you want it to be negative. And that's all there is for X plane. And Y plane, there is the gravitational force. Let's say that that's negative, and what's going down, so we'd say that that's negative because our Y is going up in positive. And there is the N and Y plus the force friction in Y. And that's all for your diagram. And so the idea is to always write down, break down your vectors into components if it is not going along your axis. So if it is not a force that looks like this, or a force that looks like this, if it has an angle compared to your axis, then you'd want to break down these vectors into components and then work from there. And I talked about angular acceleration over here because we need to know your MA as a centripetal rather than just normal A. So in this case, it's going to be a centripetal. So the net force here is always like I said, the same direction as your acceleration. In this case, it's only in the axis. The net force has to be the N and X. Take away the friction in X, which gives M times A centripetal. This one that just gives 0 because there's no motion going on in the Y plane. So if you have A centripetal, you also know that the A centripetal is v to the 2 over R, and therefore this one has to equal to M times v to the 2 over R. And the radius, it's normally given in the problem, so you will know the radius, you will know the mass if it is given, and you can look for the velocity. Or if they give you the velocity and you're looking for the mass, well, you have the radius, you have the velocity, and you have your equation for the forces. You can isolate the mass, and usually the Y, stuff in Y, if it is a banked, well, like a inclined plane like this, the stuff in Y will be given, so the mass is given, so the gravity should be given. Either way will cancel out since all these components are equal to 0. So even if you don't have the mass, it still is possible to work with these to look for the mass, if that's the question. It all depends on what the question is asking. Another thing we have to know in this chapter is the internal forces. So let's say there's block 1 and block 2. Whatever force that is acted on the block 1, it will have the same action-reaction force that way, but it will also have impact on the second block, because this force that is pushing that way will have to equal to the box 2 pushing toward 1. And that's the same thing if it were opposite like this. The force that the 2 pushes on 1 is equal to the force that's 1 pushes on 2. And however, the internal forces will depend on which object is being pushed on. So in here, 1 is being pushed on, and then here, the 2 is being pushed on. And these internal forces, these are called internal forces, are not equal to each other, depending on which box we're initially pushing. So if we're pushing on the 2 versus pushing on the 1, they will not give the same internal forces, and one will be bigger than the other, and you can prove that by calculating it. But everything else will change, will stay the same. So the gravity and the normal will always stay the same because there's no motion, there's no acceleration in the vertical plane. And there is another type of action-reaction that we should know, which is, we're going to start talking about pulleys. And pulley is a whole concept you have to understand. But if it is like this, the same similar idea applies, just that there are a bit more to it than just vertical, horizontal forces. So this is like the individual diagram. We have an individual diagram over here for 1 and an individual one for 2. And you can actually draw it all on one same diagram. On this one, for example, you can do the total, like the total body, well, the combined diagram. There's the combined diagram, which is only showing your external forces, and this one will include internal forces, but the internal forces cancel out. So these two will cancel out in the external full body diagram, because the force that's being pushed on here will not, well, the forces that are internal in here, 1 and 2, will not be drawn. You will never draw these since they cancel out physically. But you do still have the gravitational forces and the normal forces and friction force if there is. No, the friction force normally should be the other way around. So the friction force would normally look like that. And over here, it's a little bit more work, because we have a gravitational force, Fg1, and a normal force on 1 by 2. But then you also have, let's say, a friction force that way. And that friction force will have to equal and opposite on the reaction, so the box 2 force. So there must be a friction action reaction force on the box 2 as well. Let's say there is, well, not let's say, but there is a force tension over here. Let's say that's the tension 1, that's the tension 2, and we have a tension here as well. What happens is that not only does the 2 have gravity and a normal, it also has the action reaction of the normal force of the box on the second box. So it would look like this. So there's another force that is vertically pushing it down, which is the second, well, not the second, but the normal force of the box 1 on 2. Box 1 on 2, action reaction force. And the friction force that is right here will oppose this one, whereas it will be equal and opposite in magnitude for the first and second. The normal forces are what you need to understand properly. The N1 has to be equal and opposite with this one, whereas no, the N1 has to be equal and opposite with the FG1, but then there is the N1 that is on, will, if it's resting on the 2, it will have to have a force that is onto, so there's N2 floor and FG1, which is going down, and this one is normal 1/2, as well as normal on 2/1. And of course there is FG2. So this one is everything in the Y. The normal on Y/2 is equal and opposite with normal on 2/1, and the normal on the 2 by the floor is equal and opposite with the gravitational force on FG/2. But again, this one and this one will cancel. The normal on the 1/2 and the normal on 2/1 will cancel out. That's why you do not normally draw this one and this one over here on the total diagram. But if you're drawing it on the individual diagram, they do exist. And working on either individual or total diagram works either way and will give you the right answer. It's just that you have to take account of, let's say if it's a total diagram, you have to take into account T1 and T2, whereas if it's individual, you only care about T1 or only care about the T2. Talking about pulleys, there is a whole chapter about pulleys. There are 2 types of pulleys, massive and massless pulleys. Massive pulley means there is mass, and massless means there's, well, the word says no mass. And when it's no mass, it's also called the ideal pulley, where the tension coming from this way and that way will be equal in magnitude. So tension T1 will equal to tension T2. If it's a massive pulley, tension T1 does not equal to tension T2. Well, it could be equal to each other. It's just that we do not automatically, we cannot automatically tell that they are equal to each other if there is a mass, and there are other things that you have to take into account too. And the acceleration is a big part of understanding the pulleys. If it is, let's say this object is bigger. This is 2 times the mass. This one is the mass, so this one has twice the mass as the first one. The acceleration will be going this way. This is the acceleration. And another thing is that on a pulley or any type of tension, the force that is going this way, T1, is the same magnitude as the tension force going that way. This one is tension 2. So tension 2 over here and tension 2 over here is the same magnitude, and T1 going up, pointing up and lifting the box versus the tension pulling on the pulley while pulling down. They're equal in magnitude. But overall, this is accelerating this way because it's told in the question, let's say. That means over here, the acceleration is going that way. And what's important over here is that when you write your sum of forces equations, these will all be in Y because there's no motion or forces in X. You have to take account of which direction the acceleration is pointing at. But what's important is that you need to treat the acceleration as a magnitude. And what this means is T1 minus Fg equals to M1A, meaning that the tension 1, take away the gravitational force 1, will equal to the acceleration, because the acceleration has to be in the same direction as the net forces. And the net force, we know that it's T1 minus Fg, because T1 has to be bigger. So this one has to be bigger than this one, which is the gravitational force, in order to go up. Tension has to be bigger than the gravity to go up, and the acceleration is going up. So we want the equation to be T1 minus Fg. It's the contrary for the second one over here. The second pulley, it should be rather Fg2 minus T2 equals to M2A. And that is, again, because Fg has to be bigger than the tension 2 for the acceleration to be pointing towards the gravity. So that comes to the same idea as you want your force sign to be pointing towards the acceleration if it is positive, and pointing on the other side or opposing the acceleration if it is negative. Fg is pointing towards, and over here T1 is pointing towards acceleration, whereas T2 is pointing, well, opposite the acceleration, contrary, well, opposing, just opposing the acceleration. Over here Fg1 is opposing the acceleration. And that's how you write your equations. And one thing that is amazing and works well is that these accelerations, of course, are equal in magnitude. So this acceleration here and this acceleration here, they're the same acceleration because it's a pulley, and there can't be a rope that's moving faster than the other. Like the cord on this side and the cord on that side are moving at, well, accelerating at the same rate, at the same increase in velocity. So this is only working because it's a massless pulley, meaning there is no mass that's trying to restrict the movement. Masses basically means that the pulley will move freely. So the pulley moves freely. The only motions that, well, the only motions that the force can create is from the gravitational forces of the objects that has been countered by tensions. The pulley could be placed in many different ways. Let's say this one, if we were to draw the equation, write down the equations for this one. Let's say this is a 2m, that's a m. What we have is Fg2, let's say, and T2, which is opposite and equal and opposite over here in T2. T1, and that's also T1. Here there's Fg1 and there's a normal. Let's say that there is friction, just so there's some stuff to talk about. Fs or Fk, let's say it is moving and that it is accelerating that way, and that A is going that way. And we have our plane x positive over here, y positive over there. So our sum of forces in y, let's say for the 2t, T2, tension 2 for the second mass, will be Fg2 minus T2 equals to, well, ma, but this m specifically is 2m. And for x's, and that's only for the second box. So this one is only for the box 2m box. Let's say for the fx in the box m, or let's say the fy in box m. So these forces, we have tension 1 minus force K is equal to MA, where AM is the box M, so this one. We can also have an equation for F and X, so this will be for the box M again. Oh no, that was an X. Actually, I can just, this one was an X. So in Y we have, well, we should say N, the normal force of the mass, take away Fg1 is equal to 0, because we know that in the Y plane, the vertical plane, there is no acceleration. And these are useful because we know that the A here and the A here are equal to each other. So if you want to isolate this equation and put it into this equation, they will be equal to each other. And if it's a massless pulley, we also know that T1 is equal to T2 in magnitude. So by rearranging, let's say this one can be turned into T1 instead, or we can turn this into T2, and by isolating, T1 equals to 2MA, take away FG2, or rather, since there's a negative sign, just do FG2, take away 2MA is equal to T1, and that T1 you can plug inside this formula, and like that you can find A. And if they give you A, then you can look for M if that's not given, and just play with the equations, the unknowns, and what you do know. There could be an inclined plane once again with pulleys, and these are one of this is one of the biggest, I'd say, concept you should master in the mechanics chapter or the mechanics course. So let's say we have Fg and the normal and the static, or the friction, kinetic friction, let's say. And there's Fg2, and there's the tension force, there's the tension 1. If it was massless, once again, the pulley is massless, then the T1 is still equal to T2. And you can figure out everything else, but now just incorporating the angle over here. So the angle over there will have to equal to the angle here, and again that's by knowing your triangles. And if you know Fg, well, you can find the Fg in x, you can find the Fg in y, and you'd want to use your xy axis in this direction, so the diagonal x and y, because your acceleration is that way. Over here the acceleration is this way, let's say it's speeding up this way, and over here, since the string, well, the cord is being pulled in the direction of the pulley is changing the direction of the cord. Either way, the object has to accelerate in this direction, so you'd always want the axis to be in the same direction as the acceleration, which means you don't need your FGs over here, and you'd rather use these red ones in x and y, so Fg in x and Fg in y. Your normal force, however, could be found from your Fgs, but in y's as well. Your normal force in this case, so the sum of forces in y for this block over here, we have Fg in y. Actually, the normal force take away Fg in y is equal to 0, so the normal force is equal to Fg in y. And we know that Fg is from, if that was Fgy, Fgy is equal to Fg cos of theta, and Fg cos of theta is equal to the normal. Well, that's one value that I could find from that. And you can also find the force of kinetic friction, which is equal to mu k times the normal. But you know that the normal is equal to Fg cos theta. So finally, the kinetic force, friction force, will equal to mu k times Fg cos theta. And it will work as long as it is correct on your diagrams. You can find the normal force, you can find the friction force, you can find the tension force by given values for other things. Yeah, but this one is definitely something you need to understand. FG and turning it into Y component, turning it into X component. Usually it's just Y, so that you can find the normal. And once you find the normal, you can find the friction as well. So let's now talk about the banked curve. There's a car that is on a curve that is on like a racetrack, and it's like a road of racetrack like this, and they're just spinning around. They're spinning at a constant speed, but a very high speed. And in this kind of question, the acceleration don't work normally. So the gravity, the acceleration don't work like the norm. And this is all because of the centripetal acceleration. And this is a huge mistake you can make that I actually made on my final exam because I kind of forgot to revise this. This car is accelerating towards the center. And if that's the case, well, there's FG and normal. What axis would you need to use? Would you preferably be using this axis? X going that way and Y going that way. Just so all your calculations will match your acceleration vector, and therefore your sum of force vector as well. So you want your Y to be going that way, your X to be going that way. And if you do your axis properly, you will see that FG should not be broken into components. No components. Because it's already in the component form. It's already in its fullest component form in the Y. There is no FG and X like that, or FG and X, weird FG and X, or weird FG and Y like that. Those are totally wrong. Which I did on the final because I just forgot about it. So remember that if it is a banked curve and you have an acceleration to the center like this on a vertical plane, you'd want to use the proper axis, but not only that, do not break already component wise, so already aligned to the axis forces into a smaller component. That just breaks your physics. It does not work. If you did like this, FGY and FGX like that, those are wrong and you totally not need them. So what you do need to break into components is the normal force. So normal force in this case should be broken into normal in X and normal in Y. Because you can see here that the normal doesn't align parallelly align, it just doesn't align with any axis. In order for them to align, you need them to become a component. So right now, see, this one aligns with X and this one aligns with Y. And for that, you do need an angle. You have an angle here, and this angle is equal because I forgot the name about it, but their angle, they're parallel. These are parallel lines, and parallel lines was a line that goes through these two parallel lines will have an identical angle in between. And if you know this one over here is a 90 degree, then here is another angle, here is the same angle, so theta is here. And using that, we know that the nx, we can draw this here as well. This is also nx, and this is also ny and nx as well. Just take these off. If you draw it like this, you can realize that ny equals to n cos of theta, and nx is equal to n sine of theta. But not only that, the ny is equal to the fg in magnitude, because if ny is going upward and that's the only force opposing fg, well, we know that they have to be equal in magnitude, because fg, well, ny take away FG has to equal to 0. So then NY has to equal to FG. And you have that in here. Since NY is equal to FG, we know FG is equal to normal times the cos of theta. And this normal is the magnitude. This normal is the magnitude of normal. And I'm not sure if I explained it, but normal just means the force that is perpendicular to the surface. And what this means is that the FG divided by cos of theta would equal to the normal. And you can use this in your equations later on that we're going to be making. Let's make them here. In x. We are making sum of forces in x because that's where the acceleration is pointing toward. The acceleration is in the x-axis. So all the force, sum of forces in x will have to give a net force equal to the mass times the acceleration right here. And reminder that this is a centripetal acceleration. So in x we have normal in x equals to the mass times centripetal acceleration. And there's nothing else because the normal really was the only force in this case. And this was because it was a frictionless road. Not that the road was a frictionless pave, it's just that in this context, which is a context you'll always get on exams, or I'll guarantee you're gonna have this question. How can a car, at what speed can a car be driving for it to not need friction? So no need of friction, but then it's spinning around a banked curve like this. There's a curve with an angle without slipping, without flying that way or flying this way. We'll right now talk about without friction, but if there is friction, there is some difference that you have to take account of. So now we have nx equals to mac, and we also know that nx is equal to n sine of theta, and we also have that n is equal to fg divided by cos. So we have n sine of theta, which n is equal to fg, so fg divided by cos. So fg by cos theta is equal to the mass times a centripetal. And we also know that a centripetal is equal to v to the 2 over r. So then this one can be further reduced to, well, we know fg is equal to mg, mass times the gravity. We can cancel out the g's, the m's. G sine theta over cos theta is v to the 2 over r. And sine theta over cos theta can also be reduced to tan theta. And if you were looking for the velocity, let's say, we know that the velocity is equal to root of g tan theta r. Yeah. So there are many demonstrations you have to do in mechanics, but it will always make sense as long as you follow the right process. Do not break the gravity down to x and y and say that there is a y component in your drawings. The only component that do break down in this case is normal, and I made a mistake of drawing x and y gravity, and after that I said that the gravity y is equal to the normal. That is totally not true. It might seem true, but if you try testing out, mathematically it does not give the same answer. So yeah, fgy that you invent right here is not equal to the normal. Although they're parallel and they look the same, they are not. And right now let's do the same question, but with friction. There's friction. So the funny thing about friction is that it can go either way. The friction could be pointing that way, or this way. And if you do the similar, well, the exact same drawings as this one, just incorporating friction, there's nothing here about that. You just need to break it down into components. So again, your x and y should look like that, and acceleration is going that way. So you have a FG, you have a normal that you break down into components of x and y, or y and x, normal and y, normal and x. And you also have to add, just add your friction. If it's going that way, there's a friction here. But you want that also in the xy plane. So you break down into components as well. This is friction in x and friction in y. And friction in s just equals to the mu s times normal. And you can find out what Fs in x is or Fs in y is. In this case, you would want the Fs in x, so the force static friction in x, because that's this one over here. And you're basically doing a subtraction of n in x and Fs in x. So n in x, take away force friction in x, will become your mass times centripetal acceleration. This one could end up looking like this instead. And when does that happen? That's when the friction, instead of pointing upward, is pointing downward. If it is pointing downward, your components for the friction will be Fs and y like that, and Fs and x like this. You'd realize that it is pointing the same direction as the acceleration. So friction is helping. Friction is helping the acceleration, so helping the velocity, because centripetal acceleration is equal to v2 over r. If it is pointing downward, so towards, if it has an x component that is towards the acceleration, any force that's pointing towards acceleration is contributing to, like, helping the acceleration. Anything that is opposing it, like if it was pointing upward, it is reducing the acceleration. It's like taking away some vectors that will end up in the acceleration. In this case, it's adding, because that's our acceleration vector. There's an x and a y, there's an x and y in both cases. One is helping, so this one can move faster. Velocity will be faster. Velocity will be smaller. And again, if you think about it logic-wise, in like real world, think about a car that's spinning like rotating around the curved pave in a slow speed versus a faster speed. If it's slower, there must be more friction for it to not fall, right? Like, you don't want the car to fall, so there must be friction, and the friction will be acting towards the top. It will be pointing upward to oppose gravity. But then if it was spinning really fast, what happens is that you don't want to be too fast that you slip that way. And that is because if you have no force opposing your acceleration, it could be a danger in real life situation that your car will just fly away, like fly that way. And that's because acceleration is this way, and if there's too much acceleration and not enough friction to compensate for the velocity, well, then there's too much velocity compared to the a centripetal that we have, that there's not enough friction and your car can just fly away. So there is a maximum and a minimum speed you need. You'd have to follow for it to be safe, and the question often will be, what is the minimum and the maximum speed? And maximum speed for you to stay on the curve, stay on the banked curve without friction or with friction. Well, without friction, there's only an ideal speed. Ideal speed will be without friction. And if there is friction, there's a minimum that you can go at and the maximum that you can go at. And it all depends on which direction the friction is pointing at. So it could be a plus or a minus. Again, that's totally a question that will definitely be on one of your tests, pretty much guaranteed. The question of would something slip or not could be worth mentioning. Let's say there's a block, another block, and we don't know which way it's initially moving. There could be questions where you don't know pretty much anything. You don't know which way it is moving. You don't know the direction of the velocity. You don't know which way is the direction of the acceleration. And, well, you are given the mass. Let's say this is bigger. That's a bigger mass, and that's a smaller mass. What you have to know, especially with the friction coming, is that you don't even know if the friction is going this way or friction is going that way. And you don't even know if it is a kinetic friction or static friction. In these kind of problems, what you always have to do is to assume. First, assume that it's, let's say that you assume that's going to accelerate that way. If you assume that it's accelerating that way, then you will write your equations according to what you just assumed right now. And even if your assumption is wrong, it totally is fine, because if it is wrong, you will result with a negative acceleration. Your acceleration will turn out to be negative. And what does that mean? Let's say this is a tension, this is tension. If tension 1, tension 2, tension 1 take away mg1, well, that's mg, and that's x, that's y, that's theta, so that's gonna be mg1 sine of theta. Take away force of friction, because if it is moving that way, the friction does have to point that way. It's not random selection. If it is moving that way, if you assume that it's going that way, your friction will have to go that way. Actually, you do not talk about friction right now. So not knowing your friction in the question, if they don't give you which direction the friction is pointing at, then you'd first try your equation without friction, meaning that you treat the situation as if there is no friction at all to find out which direction it is going. So if there's no friction at all, just forget about the friction completely and say that that is equal to 2m in this case times the acceleration. And you do the diagram for, oh, that's not in y, that will be in x. Or you could add that the y was the normal force. The normal force, take away the fg1 is equal to 0. That's for this one. So now you know that this is just saying that n equals to fg1, but you don't use it here. For the forces in y, for the second mass, we have, so fg2, take away t2 is equal to m2a, again assuming that the acceleration is going that way. It's all assuming that the acceleration is this way. And what happens is that when you isolate when you isolate the acceleration, if the acceleration turns out to be a negative value, that means that the acceleration was not that way, it was going the other way. So what you have to do is, well, now you know that the motion with the acceleration is going this way. And if it is accelerating that way, your sum of forces will have to also point that way. And that's how you can figure out the other unknown forces. So for this one here, there's a normal, there's gravity, and there's some component over here, and there's a tension that is given, let's say, and you know that the sum of forces will be 2m times a. You don't know if the friction is going that way or this way. You will use your known net force, since F net equals to 2m times a, and you know that a is going the other way around. It's a negative. It turned out to be negative when you did it this way, so that's wrong. So this is the right acceleration. You need to then isolate your unknown vectors by using what you do already know. So T1 is opposing, so FG, in this case sine theta, take away T1, will have to equal, well, T1, take away the friction force, will have to equal to MA. And what this Fs will give will depend on what algebra gives you. So if you get, well, you know that the 2MA, the same A, is plugged in over here. You can use these variables, that's why you want all your equations written out, but you can play with FG, T2, and the mass that you already have with the mass you have over here times 2, and FG sine theta you have, T1 you'll have as well because the pulley is an ideal pulley. So the pulley is an ideal one. Tension 1 is equal to tension 2. And what you're trying to do is to find the Fs, if it's going negative or positive, and you can even find their magnitude. So everything has to do with algebra and isolating your unknown from many equations. And this is just an example case. It could be less complicated depending on how nice your teacher is. So torque is the next chapter, or the next section in the second unit. Torque is all about a force that's applied on a rotating object, or object that will rotate from a force. Let's say I push a door. This is a door from the top view, and if I'm pushing it this way, then it will rotate. It will move about the pivot. This is the pivot. The formula for torque is R cross F, and it's a cross, not a multiplication. And that matters because what we're trying to do is, this is the R, and of course that's the force, but we're trying to find the torque, meaning the movement, the force, the sum of force in an angular motion, where we talk about, where we care about the distance from which the force is applied from the pivot, and the amount of force, of course. In this one, it's going to be Newton, like a normal force that we're talking about. And it always is a perpendicular relationship between the R and the F, if you want to use this equation. If they are not perpendicular, let's say there's a bar again, and you're pushing it like this. You could push a door like that, or a bar. That's the R, meaning the distance from where the force is applied. And this is the F, but there's an angle between them. What's going to happen is that the torque will now equal to R times F sine of theta. And this is just a multiplication. So this is applying your angle in between the force and the R, a sine of something. But then if you realize over here we didn't need to care about the angle because it was perpendicular. The sine of 90 just gives 1. So multiplying by 1 just isn't necessary to write. That's why if the torque, or the force applied to an object that is turning, that is rotating, was a perpendicular force compared to the surface of the object, then you do not need any sine or other complication, because it could be rewritten as plus or minus Rx Fy plus or minus Ry Fx. This just means, let's say you have a R that way, because this is your bar that you're trying to push. So this is a lever, let's say, that you're trying to press down, and you're pressing it with a force that way. This is your force that you're applying to, and there is an angle in between them. All you want to do here is to break them down into R components in X and F components in X, and r components in y and f components in y. So there's the y component, x component, and you'd be wanting to use x and y and x because you want them to be perpendicular. Because this is the r and x, and that's the f and y. They are perpendicular to each other. And similarly, the r and y and the f and x are also perpendicular to each other. And we are using the perpendicular stuff because, again, the sine of theta of 90 degrees just equal to 1. So all you have to do is an addition of this torque and this torque. And we're saying plus or minus because torque is a rotational physics that you have to add signs accordingly. And the signs are plus k or minus k. And plus k's are usually counterclockwise and negative k are usually clockwise. And I'm saying usually because it's basically random people that decided that something is plus or minus. It's kind of the same thing as who decided that the right is plus and the left is negative. This has to do with the right thumb rule. So you have a hand and you have your thumbs, and your fingers should be pointing toward the R, and you will curve your fingers to where the force is, and your thumb will indicate the direction of your torque, the torque direction. Where if it was pointing upward, let's say, then it's going to be a positive J. If it's pointing downward, it will be a negative J. But usually, torques will be into the page or out, like coming out of the page. If it's into the page, then it is a negative K. And out of the page would be a positive K. This could be better explained through visual explanation, so I just stop here. Just know that there is K values in terms of direction. There's plenty of videos on YouTube or something that has explanation about right hand rule for torques and directions of the torques. There are many conceptual questions where there's like a bar and there are many forces that are acting on the bar. Let's say a force that is force 1. There is a force that is pointing that way. Force 2. Another force like this. Force 3. A force that is right here, but double in magnitude. And a force that is somewhere here. Also double in magnitude. 6. And they will tell you to place them in increasing order. I won't be doing it, but all you have to do is RF. Torque is equal to the RF. And the R is whatever distance this is. Every time you just apply the right R. The F, of course, is just the magnitude. However, you will add sine of theta if there is an angle between them that is not 90. And here there is an angle that is 90. There's 90. And over here there's a theta here. There's a theta here. You'd always want to use the smallest angle between them. The smallest angle between them. Not this one or like that one. You always use the smallest angle between the R and the F. And by doing that, you will have the magnitude of the torques for each of the forces. And from there, just look at the fractional coefficient and place them in the increasing order. If I remember well, here it was F5 smaller than F6. Well, the torques. So T5, T6 equal to T3. And then oh no. And then, yeah, that's pretty much it. I'm not sure if this is right. Just try to do it. And the whole concept is about R, F, and sine of theta. There's also Newton's law, second law, in rotation instead, and that's with the torque net instead of force net. Torque net, basically the sum of all torques is equal to inertia times alpha, and the torque will have the same direction as the alpha, and alpha is the acceleration in angular form. So let's say there's an angular rotation, it's rotating and it's getting faster or slower. At an instant, there is the change of this angular velocity, and all our contexts would have a constant angular acceleration, so that this equations would work with given velocities, as the velocity, angular velocity is changing at the same rate. I is a new thing that you see for the first time in this chapter, is inertia. Or I should say moment of inertia. And moment of inertia is comparatively a mass that you have to move. And if it is a point mass, meaning it's just a dot that is spinning around, its inertia would be mr squared. And if you know that F equals to ma, well, if I tell you that torque equals to I alpha, it's basically the same principle. One just in linear and the other one in rotational. When it comes to rotational, the mass will no longer just be a mass, but the mass times other stuff, usually a r squared, but it could have other coefficients like half mr squared for a disk or a cylinder, 3/4 mr squared, 2/5 mr squared, etc., depending on what the object looks like. And every time the question will usually give you the equation for the inertia, but inertia just means how hard it is, how much torque it takes to spin. And this one is just angular acceleration. There could be given questions like a dumbbell that has weights around it and another dumbbell that has the same weights, but we're spinning it from here. What happens in this kind of situation is that, well, the inertia for each case will be slightly different. In here, let's say they have identical mass, so this is a r distance, this is a r distance, but here it's a 2r distance. So inertia here will be mr squared plus mr squared, because each of them is mass m, and r squared because the inertia for each of them is just, it's a point mass, meaning its shape is irrelevant, it's just a point of mass. We'll just give it 2mr squared. However, over here, if the distance is 2r and we're pivoting about this point, well, if it's pivoting about this point, this mass will not matter. This mass we do not take in account, so it does not have any inertia that has to do with the torque, or has to do with the motion in context, because if it's spinning about itself, the r is equal to 0. So mr squared will just equal to 0 since the r is 0. Either way, if it is pivoting around an object, that object has no inertia, where the mass has nothing to do in the rotational system. So inertia here will be m times 2r squared, which makes it become m times 4r squared since we distribute the 2, giving 4mr squared. And that's a lot bigger than this because the distance is dominant since it's squared. as the formula goes like mr squared, the r is dominant compared to the m because it is square, so it has more impact to the inertia if it changes. And in this case it grew, so it grew significantly larger. If the r were to become smaller, so if the r, let's say, became a third or something, then the inertia will become smaller definitely. The inertia will decrease because, again, it is dominant, and how much it decreases will be significantly larger than what the mass is doing. The torque equals to I alpha is used in contexts like a disc is spinning and suddenly a brake, this is a brake is applied on the spinning disc or wheel. It's spinning and the sudden disc will apply, a sudden brake will apply a torque. There's a torque applied onto it. And it is accelerating, well, decelerating at the given rate, where we know that the final angular velocity is 0, and the initial angular velocity was, I don't know, let's say 32 rads per second. We can first of all find alpha from the equation. Given that the t is given, let's say 50 seconds. And you can find your alpha, and with the alpha you can look for the torque. Because you plug in your alpha, and the inertia in this case will be the inertia of the disk. So inertia of the disk is half mr squared as formula. Half mr squared times whatever that alpha is that you found. You multiply them together, and there is no sign of any angle over here that matters because the force and the radius are perpendicular to each other, and the force looks like this, although it is seemingly seemingly parallel, horizontal to the radius, but that is not the case because the friction force is what is stopping the disk. The friction force is perpendicular to the brake, so the force indeed is perpendicular. So we'll have a torque equals to your inertia that you found times the alpha that you found times sine of theta if you want to write that, but sine of 90 degrees is just 1. So times 1, which you don't need to write, and you can find your torque. There's nothing too much complicated in the torque as long as you know the formula, as long as you know this formula, and as long as you know what inertia is. Everything is very simple. Often there is a question that you will get about a cylinder, and there's rope going around the cylinder, and that rope is hanging a bucket, and that bucket will fall, and you're asked to find the torque that the bucket applied onto the cylinder. What you have to do is use your kinematics equation, meaning your it could be velocity final equals to initial final plus at. You could use instead the angular stuff. You could use different formulas, and depending on what you're asked or are given, you can use theta instead. And all this is to say that you can find your t equals to I times alpha in many ways. First of all, the inertia will just be the inertia of this cylinder, since that's what we're turning. So it will once again be mr squared half. And alpha, like I said, could be found from whichever of these equations that you are given. And you're likely given the amount of time it took for the bucket to fall, its initial speed, rotational or linear, And we know that, well, no, we know that initial speed is 0 because it's falling from rest. And we're given the time, we're given that acceleration is 9.81, or maybe you're not given, you just have to know that the gravity of Earth is acceleration over here in this case. And in many ways you can come to a conclusion of what the alpha is, applying one of these or other formulas, and find out what the torque is applied. It's really fairly simple. Now you can use the forces diagram to go like Fg is equal to the tension, and that this tension is what's applied onto the cylinder, which is the force. You could totally do that because T equals to R cross F, and in this case F is just the tension, so you can look for the torque this way. And what this means is that you need to know the tension from gravity, and you then need the acceleration because Fg take away T has to equal to m times acceleration. You can find acceleration from, again, one of these kinematics equation to plug in and find what T is. If you found T is, you can plug into the torque equation to find your torque, given that you know the radius, which is just the radius of the cylinder. And if you use the radius and the tension force, you don't need the inertia. You no longer need the inertia because you have the force that is applied on the cylinder. So there are two ways to do this question. So one more thing is center of mass. Center of mass is, like the word says, there's a mass and there's a center. And what's funny about this is that when an object of weird shape flies, what we're drawing, like the trajectory that I just drew right now, is the trajectory of the center only. The center will always follow the trajectory that we are calculating, regardless of what it looks like. Let's say it's a stick instead, then its center of mass will be right here. And it's important to know the center of masses because there could be a situation where there is many components. Let's say that there is 2 beams and a boy standing on it. And we want to know the, let's say, the distance of which the boy can stand as far as he wants so that the beam doesn't tilt. No tilt type of question. So here what you have to know is, of course, there's the torque concept, but the torque for the center of mass, more precisely. The center of mass could be here, meaning that the center of the beam itself is of course in the middle because it's a uniform beam, but then the boy adds up to this mass. So from here, let's say the boy is at a center of mass of somewhere here because we have the equation x center of mass equals to all of the sum of mass times its position divided by the total mass. So total mass, or just m total. And what this is doing is from a distance 0 that you put as a reference point, and let's say this is 2 meters, you have a certain amount of mass that you would divide by the total mass. Let's say there is another mass over here, to find out where the new center of mass is. So right now this mass is at 2 meters, but there is also a mass, let's say that's 5 kilograms over here, and this guy's 2 kilograms. What we're trying to do with this equation is to find the new mass. It would likely be somewhere here, that represents both these masses with the appropriate distance from the center, well, from the reference point. And we do that with this equation. The x center of mass would be the sum of all masses times its position. So in this case would be 2 kilograms times 2 meters plus 5 kilograms times 0 meter divided by 7 kilogram, which is the total mass. And that will give you something like, I don't know, I'd estimate it to be like at 0.78 maybe. You just need to plug it in to find out. But that position will be your center of mass position, xcm, which can be used for your torques R, because that could be your new R distance. Let's say if it was here. And I didn't show a concrete example of this, but the whole point is to show you what a center of mass is. So cm r cm is equal to mi r I divided by mass total. And this can be broken down into x and the y's. So xcm equals to, well, same thing, times xi over mass total, and ycm is equal to total mi times y. You don't need the x to shuffle on the x, divided by m total. All of this is to say from what distance ratio are these masses significant. So the significance of these masses compared to its distance. And let's just do an example for center of mass visually. Let's say there is a block this big, and its center of mass will of course be at the center because it's a uniform beam. But then we cut out a piece. We cut out this piece over here, which also has a center of mass right there. What's going to happen is that you will subtract the position center mass of the original one by the subtracting one. And that would look like a diagram that says M. Actually, we can use the area since they are uniform. So area, the x, the y, the a and x, and the a and y. So area can be used because if it is with the same linear mass density, you can use m on L, whereas if it's a density, you can use m on A, meaning that the surface mass density is always well proportional to the mass itself. So in two-dimensional, we have density equals to m over A. And given that the area, let's say it has an area of 225, this has x coordinate of 37.5, a y coordinate of 15, and that's the blue block. For the red block, let's say we have a 78.5 and then 10 centimeter. We'll move the block. We'll move the block to the center actually. So let's say the block is rather over here. Let's say it's a circle over here. And we have the xy coordinates of 10. What we do is ax, well, it's just the area times the x, which gives 8.4. No. 84375, and over here is 33750, and then you will find your areas for each, well, area times the x position, area times the y position, and the key here is to just take away. So this is the same thing as doing x center of mass is equal to the sum of x's divided by total mass. It's just that instead of using distance, we're using area. And by doing that, we can cut out this piece from the blue square, and the blue square will now look like a blue square with a hole. So everything else is still there, but just the hole is gone. You will get a new x and a values, a new ax and a values, which then you'll divide by the total area. So the ax divided by total area and the ay divided by total area. And these each will give your coordinates x and y for your new center of mass. It's the same principle as the distance, but instead of using just distance like x's, we are given a box with like a rectangle and a subtracting area to find out the new center of mass. Oh my god. And the new center of mass should move a little bit to this side, because if it's losing some area over here, then it has to, like the center of mass has to move towards where there is more material. So it's all about where the material is. Coming back to the boy and the beam, walking beam, the torque works for all the torques that are applied on the beam. So the sum of torque, which is equal to I alpha of the beam, because the beam is what's spinning if it does spin. The sum of torque is equal to torque 1 plus or minus torque 2 plus or minus torque 3 plus or minus, etc. And this plus or minus again is by using the right hand rule. In our case, we have a force over here pushing it upward, another force pushing upward, another pushing upward, and the boy is pushing downward. So I should try like this. What happens is that from here there is a R and there's another R going that way with its respective forces. So this one, let's say, is a bar force, a FB1. Let's say this is a FB. Actually, this is FB1. This is actually FB2. And this one is the FG of the boy. Where if you want to find the net torque, we have a negative FB times R, which is 0, because the R distance from the pivot is 0 over here. So there's no torque. And looking at the second beam, we have it's a positive FB2 times R, which is this R over here. And the boy is going downward, so if you use the right hand rule, it will be a negative FG boy times the second R. So this is 2R. And all of that would have to equal to I alpha. Where if it is not moving, then alpha will be 0. Meaning that the beam doesn't tilt. If the beam doesn't tilt, all of that has to equal to 0. So now we know that F2R has to equal to FG boy times 2R. And from this, what you can tell is the force of the beam, primarily. You can figure out the force beam too. So the force that this beam is pushing upward by canceling things out, and you know what FG of boy is, multiply it by 2. This will give you the FB component. And they could ask you how far can the boy move so that the beam doesn't tilt. And that answer is just going to be when the F beam 1 is equal to 0. And that comes from logic, actually, because if you have the boy standing like this and you want to know at what distance it is from the second beam, there has to be a force this way, have force that way, but absolutely no force pushing it upward anymore. Because as soon as there is too much force going this way that cannot be compensated by this force, it will tilt. So at the verge of it tilting, right before it tilts, this force is equal to 0. Just need to set that equal to 0, and you can find your new x value. To do that, you will just make your torque from about this point. So this is your about point pivot. Set your torque equal to RF, where R is the location of FB2, and you'll be doing your add another torque, same thing, to find what that X is, where X is the R for the FG of boy. So X is the R distance times FG, where the torque of this one being 0 and this one being the only torque balance out to become a 0. And of course this force is 0 because it's not touching the beam anymore at the verge of it tilting. So one last example that we're gonna see here is the ladder. So we're gonna have a question about ladder that is 50 kilogram, and its center is at the center of the ladder because it's a uniform ladder. And let's say that one is 400 Newton at 53 degree. And they will ask you what the normal of the floor is and what the normal of the wall is. This one can be solved by torque because it is a pivot of a beam, which is a ladder in this case, where the torque has to be equal to 0 because there's no acceleration, so alpha is equal to 0, where t is equal to inertia alpha. And they could even add a human at, I don't know, like at 3 meters of the ladder. The idea of this kind of question is to use torque equations and your geometries. So there's R over here with a force Fg over here, and you even have a R for the human, and the human is also pressing a Fg of its own, and all of this has to add up, the sum of torque has to add up to 0. And we also have a normal on the wall, so not just the human torque and the mass of the ladder torque, but also adding the normal of the wall torque, which will be R cross F of, in this case, that's the R, so the R over here will be this one, that's the R, and the normal force will be like this, normal of the wall. It's all about adding up forces with respect to your pivot point that you choose, and you can choose any pivot point because it all works equally as long as it's a motion as long as it's a 0 motion. Well, there is always going to be no acceleration in these kind of problems. Another thing is your normal about the hinge questions. Normal about the hinge questions means the normal that a pivot point like this, but that does not move. Let's say there's a beam like this and there's a lamp, has on the wall or on a beam like this one, it's a pole, and there is a normal force going this way, a normal force going that way, normal in X and normal in Y, where the total normal is going to look like this. And in many exam questions, they will ask you, what is the total normal magnitude and direction. To find that, all you need to do is to break your forces in components. So this is Ty, this is Tx, and this one is just Fg, which is an x. And you could have other objects that are hanging. You can use torque to find out their either the R or the F. Usually you need to find the force, the gravitational force that it is acting on. Let's say it's only one object and the center of mass of the beam, because the beam has mass. So there are Fg1 and there's another Fg, and the torque will be again plus or minus Rf plus or minus Rf, where F could be a Fg, it could be another tension force like this one. But if there is an angle between them, make sure to include the sine of theta into your torque equation. Find the net torque, and you can find your missing forces if it is not given. And after that is just free body diagram. Free body diagram meaning, let's say if I redraw it, that you have a force going this way that you know, a force going that way that you know, and a component of this force and another component of this force of the tension. Whatever that sums up, that after your sum of all forces in X, the leftover is going to have to equal to the norm at the hinge, because the system is not moving. If the system is not moving, all forces, sum of all forces F net has to equal to 0, so that there's no acceleration. So sum of all forces in Y is equal to the normal in Y at the hinge, so at the hinge right here. And the sum of all forces in X is going to equal to the normal at the hinge in X. And that's it for the second unit.